Buoyancy is simply a measurement of the upward force an object experiences when that object is placed in a fluid. To understand why buoyancy exists, it's helpful to visualize a scene in a crowded subway or a bus. You can imagine that if there were a crowded subway, totally packed, and then a large gentleman tries to squeeze into the subway. As he does that, he's going to push other people out of the way. These people in this crowded train will likely get annoyed, and they will attempt to move back into their original position. As these people try to squeeze back into their original position, they're going to exert a force on the gentleman who tried to get in. Essentially, the people are crowding the large man, pushing him out of the subway because they want to return to their original position. And that's what happens in a fluid. As an object is pushed down into a fluid, it's going to have the exact same experience as a large man entering a crowded subway. As the object is pushed down into the fluid is pushed out of the way. We call this displacement. Displaced fluids are going to attempt to push back to regain their original position, and that creates an upward force. We calculate that upward force by multiplying the density of the fluid times the volume of fluid that was displaced times the force of gravity. So when you have a boat in water, there are a couple of forces that are at play. First, the boat obviously has mass. So we have the mass of the boat times gravity pushing down, which is the density of the fluid times the volume of fluid that's pushed out of the way times gravity, and that's pushing up. When something floats, it is because these two equations are equal. The force pushing up is equal to the force pushing down. There's one more equation to be aware of, and that is how we measure the mass of a fluid. The mass of a fluid is simply the density of the fluid times the volume. We could plug that into this equation here, and you could write the equation as the mass of the fluid times gravity. That's going to be equal to the mass of the boat times gravity. The gravities cancel out, and you're left with the mass of the fluid displaced is equal to the mass of the boat. If you could somehow gather up the water that was displaced by the shape of the boat, it would have the exact same mass as the entire boat. Now, just because something isn't floating doesn't mean there isn't a buoyant force. In this picture, we have a bunch of Marines in an exercise where they're not allowed to fully swim. They still have mass, so of course they still have their mass times their gravity pushing them down. And since they're in a fluid, they also have the buoyant force, which is the density of the fluid times the volume displaced times gravity, and that is pushing them up. But the buoyant force in this case just simply isn't enough to make them fully float. Instead, the Marines simply feel lighter. And that's why the Marine on the right can appear to jump 2 feet in the air. That's something he probably couldn't do on land, and he can do that because it feels like he weighs less. To calculate his new weight that he experiences, you would simply take the mass times the gravity pushing him down and subtract the buoyant force, or density times volume times gravity, and that will give you the new weight that he experiences underwater. So here's a fairly standard buoyancy problem. We have an object that is submerged in the fluid. The object has a mass of 15 grams. However, when it's in the fluid, it appears to lose 5 grams. That's because of the upward force, which is of course caused by buoyancy, which is the density of the fluid times the volume displaced times the force of gravity. And that's exerting an upward force of 5 grams, so the object appears to only weigh 10 grams in the fluid. We know from previous examples that when an object is submerged in a fluid, the mass times the gravity of the object, that is the force pushing down, that's going to be equal to the density times the volume times the gravity of the fluid pushing up. In other words, the mass of the object is also equal to the mass of the fluid displaced. So hypothetically, if we assume this object has a volume of 1 cubic centimeter, that means the density of the object is 15 grams per 1 cubic centimeter, and the density of the fluid is only 5 grams per cubic centimeter. Since 15 is equal to 3 times 5, then we can say that the object must be 3 times as dense as the fluid. And they tell us the fluid has a density of 0.7. That must mean the object must have a density of 2.1. In this next example, we have a styrofoam block floating in some water. And on top of the styrofoam block is a brick that weighs 2.5 kilograms. In a physics problem where they give you a substance that's clearly very, very light, like styrofoam or a feather or a beach ball, what the problem really wants you to do is to ignore the weight of that object. So in this case, the only mass we're concerned about is the mass of the brick. Since the brick is pushing down with a weight of 2.5 kilograms, we know the mass of the water displaced must also be 2.5 kilograms. Well, you've probably heard that water has a specific gravity of 1. What that means is that 1 liter of water weighs exactly 1 kilogram. So if we need to displace 2.5 kilograms of water, we're simply displacing 2.5 liters of water. So now we know that 2.5 liters are displaced by the styrofoam. But that's only half the styrofoam. We have half in the water and half out of the water. So that means that we have 2.5 liters below the surface and 2.5 liters above the surface, which means the total volume of the block is 5 liters.